All right. So how's everyone doing? Still awake? All right. We'll see. All right. So good afternoon, everyone. Welcome to this presentation titled "Machine Learning Belongs in a Museum." My name is Sam Gomez. I am a Microsoft MVP. I work as a client partner for a software consulting company called Jenica. You can check us out at jenica.com. And when I'm not doing something technology related, I like to spend time with my wife and my two kids. Love to play video games, watch movies, and anything soccer related. Don't get me started on that. So you can connect with me at X, I guess, formerly Twitter, @thesoccerdev. And you can also connect with me on LinkedIn if you have any questions about this presentation or any other topics on AI and ML, specifically on the Azure ecosystem. We'd love to connect. We'd love to help you out. Feel free to ask questions during the presentation. I'll try my best to answer them. And also, there's a Discord channel. If I don't get to your questions during the session, I will definitely do my best to answer them afterwards. All right, so the agenda for this presentation, we're going to do a project overview. We're going to look at what the goal of the project, why the motivations behind the project. We're going to look at a couple concepts that are going to be important during the presentation, and then we're going to look at what we did, how we solved the problem. We're going to look at some of the tools that we used during this project in case that you guys are working on a similar project, so you have some suggestions. And then we're going to look at lessons learned. So hopefully this is something that will be useful to you, whether you're working on a machine learning project at the moment, or you're thinking about doing something on the side, or you're about to start a machine learning project. Any feedback that you have, please let me know. Our intention as speakers is always to present something that is helpful to you. All right, let's dive right into it. I'm gonna go a little bit fast at one point because last time I did a rehearsal, it took me about an hour to go. So I wanna make sure there's time for questions. So the objective of this project is to build a system that is backed by a machine learning model or models that is able to maintain the temperature and humidity conditions in different areas of a museum, while at the same time, minimizing energy consumption. For this particular project, we partnered with a company called Ameresco, and they do energy efficiency projects like this one. So they were our partners in this endeavor. So what are the motivations behind the project? First of all, the museum is trying to be a little bit more environmentally friendly, so they're trying to reduce their carbon footprint. Obviously, if you own a house or you're paying utilities when you're renting, you know that heating and cooling your house is one of the biggest culprits in your energy bill. So if you reduce the energy consumption, you're obviously gonna save some money. And then one thing that I never really thought about when I visited museums is that a lot of the time, the pieces that they have on display, they don't own them. They're being lent by other museums or private collectors. And there's usually some sort of agreement, obviously, that they have to take care of the pieces, and the conditions in the rooms are part of that. You don't want a painting that is, centuries old or whatever the case may be to have some damage because the room is way too humid or way too hot, way too cold. I didn't put it on the slides, but obviously they also want to make sure that the visitors are comfortable. They don't want you sweating in there if you're visiting the museum. So another motivation behind it. So how does this process work, or how did it work before this project started? This is a very accurate drawing of what the building engineers look like in the museum. So they are monitoring the conditions in the different rooms with their control system. I don't know if anyone recognizes the style of the drawing. This is a drawing by the amazing David Neal, who has a session in the next time slot. Amazing presenter, amazing artist. So if you're interested, go see his talk. Very recommended. So it is a manual process. They have a control system. They're looking at it and the entire time, making sure that the conditions are satisfied. And if those conditions are not satisfied, they default to a safe temperature, which in this case is 58 degrees Fahrenheit. So keep that data in mind. It's going to come into play in a little bit when we talk about what we did. So this is a piece of equipment that we are interacting with at the museum. So this is called an air handler. So this is a screenshot from that control system that I just talked about that the engineers are monitoring. So it has temperature, it has outside conditions as well, because the air handler, if you look at the bottom right here, they can pull air from the outside to kind of circulate, make sure that there's fresh air at all times in the different rooms. They can also heat up the air or cool the air, depending on the conditions. And that's what we're trying to avoid. We're trying to avoid having to do anything to the air that is circulating from the outside and from the room. The perfect scenario in this case is that just recirculating the air, you don't have to do any heating, you don't have to do any cooling. When I talked to a friend of mine about the project not that long ago, the question came up about, well, if they have this control system, can't the control system do something like that? Can it manage all these conditions? And the answer is yes, but it would be a more traditional approach of building a set of rules, basically a bunch of if statements that would try to control all the different conditions that you can encounter during the day. And if you're from Ohio, you know that the weather, does not cooperate with an approach like that. Now, I know that, I don't know if you guys seen this, but there's a lot of jokes out there that machine learning is just a bunch of if statements. When we were having that conversation, that came to mind. But if you've worked on a machine learning project, and you know that there's much more to machine learning than a bunch of if statements. But still, just made me laugh when I looked at that image. So 3 terms that I'm going to be using a lot throughout the session. First one is discharge air temperature. So that is the temperature that is coming out of the vents of an air conditioning system. So right now, when the AC is on, the air that is coming to the room, it has a specific temperature. Discharge air humidity or supply air humidity, you're going to see it both ways. I forgot to fix one of the slides. That is the humidity that air has. So those two are going to be very important. And the discharge air temperature, that is what we are trying to control. That is the value that we're trying to predict. We're trying to predict the ideal value that will keep those conditions in check. And finally, when I say humidity, I am talking about the humidity in a particular room. So the air that is coming into this room has a certain humidity, and there's a humidity already or humidity value in this room at the moment. So those are 2 different concepts. All right, so let's dive right into it. What did we do? How did we solve this problem? So by we mean Jenica, when we came into the project, there was already a prototype process and a prototype model that was trying to accomplish the goal that we just talked about. And this is what it kind of looked like at a high-level overview. So we have a software that is called Easy Edge, which is the cloud that you have up there that is a gateway between the sensors and an Azure IoT Hub instance. The data that is coming from the sensors is stored in a blob container in Azure, and then it goes through a compute resource, or it was going through a compute resource that had the process of creating those predictions. We'll get into that in a little bit more. Then the predictions are coming out of that compute. They're being stored in a different blob container so that we can reference them later. And then there's a function that is looking for those results, for those predictions. It's putting them into an archive, and it's also sending it back to Azure IoT Hub so it can make it all the way back to the building or the air handler. So the problem is that the compute, the process that you see in the middle that is generating the predictions, this is what it was doing. Every 15 minutes, it was going to that Azure blob container, getting the last 90 days of data for that particular handler, and training the model in coming up with a prediction every 15 minutes. So the cost of getting all that data from Azure blob storage usually is pretty cheap, but not if you're hitting it every 15 minutes and you're getting a ton of files out of it. The other problem with this approach was that the models themselves were only using 2 features from, I can't remember what the number is, but all the features available, they were only using 2 to try to come up with a prediction. So the values that we were trying to discharge, they were not efficient enough. They were not saving enough money. They were not generating enough savings. So, and we did this evaluation because obviously we were trying to reuse as much as we could of the existing process because we had to deliver something quickly because there was already a little bit of a delay in there. So we were trying to speed it up, see what we could reuse. Obviously, if your critical piece cannot be reused, then we kind of went back to the drawing board, and we took the chance or took advantage to talk to our partners and figure out what else could we improve apart from the models, which is the obvious thing. So models with more features, more efficient models. We also wanted to do, or we needed to have separate processes for each air handler. So all these rooms, these areas of the museum obviously are independent. We want to be able to turn these processes on or off as needed. So if there's maintenance in a particular area, there's no need to have that process running at that particular point in time. We want to be able to say, okay, shut down this gallery. We don't need that running at the moment. We also want to be able to increase the temperature gradually. We don't want to jump 2 or 3 degrees because in this kind of project, in this kind of situation, even half of a degree can throw us into a cycle of warming and cooling that is also not going to be efficient. So we want to be able to just increase the temperature a little bit every time that we do a prediction. We also want to have improved logging. Before, that compute resource was just a black box, basically, where we couldn't see anything that was happening. Well, we could. You logged into the compute and you went to the logs, but it was just very cumbersome. And finally, we wanted to have some reporting so that analysis could be done about whether we were saving enough money or not. Now, a few challenges to consider when building this system was the data access. Right now, again, everything was stored in blob storage. We wanted to have something a little bit more, not just accessible, but something that we could run analytics on. The data point names, so the names of the fields that were coming from the sensors, they were all over the place. There was no naming convention, so we needed a process that would standardize that. And the other challenge that we had to take into consideration is that the sensor data was transmitted every 5 minutes, but the prediction process only ran every 15 minutes. So we needed a way to kind of accumulate all that data so that every 15 minutes we would only get the latest data from the sensors. All right. So let's look at the first one, which is the improved models. What approach did we take? So the first thing that we tried to do, okay, we already said that the discharge air temperature is what we are trying to predict. So classic regression problem, where you have different features, we're trying to get to a discharge air temperature number, so let's try to do that. Now, there was an obvious issue with trying that approach, and can anyone guess what that problem would be? The problem was that, as I said, the default temperature or the default behavior was to put the discharge air temperature to 58 degrees. So the majority of our training data had discharge air temperatures that were around 58 degrees. So we knew going in with this approach that the predictions were not going to be as good as we needed them. But the idea, or what we were trying to do, is we were trying to add some rules after the prediction to try to modify the temperature, hopefully get some data that we could use to retrain the model by itself without all those rules outside. So we tried it, we turned it on, and obviously we had some issues apart from the one that I mentioned. First of all, big temperature changes. And when I say big, I'm not just talking about some temperature changes 2 degrees. That is a lot in this kind of situation, which surprised me, because it doesn't sound like a lot. But in this kind of situation, even half a degree sometimes can throw the conditions, out of whack. Some features were not needed, so we were using things like the month or the time of the day, but we know that with weather, you can have a very warm day in the fall or something really cold in the summer, something like that. So things like the time of the day, the month, is not something that we needed to have. When we did the analysis first, we saw that it didn't have a lot of relevance, but we still included them since it was really our first try. And then finally, like I said, it was too conservative. It wasn't going as high as we wanted it to be, and it wasn't generating the savings that we wanted. So because of that, we try to put those rules around that would update those values, those predictions. But then what we ended up is we started to run into the issue that we were just putting way too many rules outside. We ended up with something like this, that we were defeating the purpose of using machine learning model in order to do this prediction. If you have a ton of if statements that we were trying to adjust that prediction, it's kind of pointless. All right, so we went back to the drawing board, and we looked at the data. We had already analyzed the data. So what other value could we predict that is important for this process and that might get us a little bit better results? And that was predicting the humidity in the room. That's one of the things that we want to control. So let's see if we can do it that way. Now, the humidity in a room, it has a very close relationship with the humidity that is coming from the air, from the vents. So what we actually had to end up doing was two models. One model to predict the discharge air humidity or the supply air humidity from the air, and another one to use that as an input to try to determine what would be the humidity in the room. If we increase 0.5 degree, what is that going to do to the humidity in the particular zone? So, high-level overview, what the process looks like is we get the current conditions of the room, and then we decide, okay, do we need to warm up? So we're within the threshold, so we have the ability to increase the temperature a little bit. Or if humidity or temperature is not in the threshold, then we cool down. And then once we cool down, then we try to predict the supplier humidity, and then we try to predict the humidity as well, just 0.5 degree. And if all the conditions hold, then we try to go up by 1 degree. If the conditions don't hold, then we leave it at 0.5 degree. Sometimes we even don't increase it at all. We just keep the same temperature. But 1 degree is, at most, every 15 minutes is what we are going to increase. Again, that is something that came up from that first scenario where we saw that just 1 degree, we didn't need to go higher. Otherwise, we were going to get on that loop where we were going to try to heat and cool at the same time, or not at the same time, but right after each other. All right, so one of the other things that we were trying to do, if you recall, is we wanted separate processes. So we wanted to be able to turn off those processes on demand for different areas. So we just use Azure Functions. We put our machine learning models behind an API so that we could call them. We can also test them whenever we want. Instead of being in a black box that we didn't really have access to. So there's one Azure function per air handler. Some of them share the same model, but some of them we had to create different models because the air handlers are different. Some of them are bigger. Some of them don't have all the inputs. So we did have to create a couple different machine learning models. There's also specific logic because some areas have offices, so we want to keep those probably a little cooler than some of the areas of the museum. So having those Azure functions allowed us to apply that sort of logic. And then we are also logging different conditions. So we want to be able to tell if we're missing any data. If you're dealing with sensors, that are out there in the wild, you'll see that more often than not, you're going to miss data. So you need to account for that. You need to make sure that you have some conditions for that. We also want to document whether we're warming up or cooling down. That will help us with the troubleshooting. The reason why we're warming up or cooling down. And then finally, what is the predicted discharge air temperature? So all the logging that we're doing is basically helping us troubleshoot if we ever encounter an issue. So what the project looks like, or what the architecture looks like at a very high level, is we still kept Easy Edge, which is our gateway that we need between the sensors and IoT Hub. We're still storing the data in blob storage, but because we're not accessing it every 15 minutes, we don't have the issue with cost that we had before. And we're also storing the data in Cosmos DB so that we can run the analytics that we want to do. Now that Azure function next to Cosmos, that we are using to standardize the data. If you recall, there was a challenge that all the points were named differently in different air handlers. So that's basically putting all in a standardized format. That goes to a cache resource so that our prediction function can get the data from there. And then we are still storing everything, or we're still archiving everything in case that we need to get back to that and we need to run analytics, we need to retrain, whatever we need that data for, it's there for us. The rest of the process, we kept some of that, we could reuse some of that. So we send the data back to Azure IoT Hub, and then that makes it back to the building, to the air handler. All right. Before I continue, are there any questions before I move on? Yeah, did you ask how big? The question was how big is the data? Are you talking about the training data that we use, or? So the last training run that we did was about, I think, 80,000 records. So in this case, in this scenario, we didn't need that much, but it's always going to vary, and it's always going to depend on the type of process that you're running and the type of problem that you're approaching. But in this case, with just in the number of thousands, we were able to get a model that worked pretty well, and we're going to see that in the next few slides. Any other questions? All right, so let's look at the some results that we took last year. So this is a project that we actually worked on last year. Started in August, finished around December. We had to pause because some work needed to be done in the building for the control system, and we're actually in sort of a phase 2, evaluating all the results and trying to improve even more. But as you can see, this is one of the air handlers. The models didn't run the entire time because there were times where the conditions did not hold. So that's part of the troubleshooting that we're doing, part of the analysis that we're doing, trying to figure out how to make them even better. But it was still a very high percentage when the models were on, and also a high percentage when the humidity is satisfied, which you can see in the last column. This is a graph of the discharge air temperature. So you can see all the way on the left, the manual process. You can see that the values are all around the same area, around 58 degrees. And then once we turn the model, that's where you see all that back and forth, because it's trying to, accounting for all those conditions, trying to find that sweet spot that we need. Now, this is a graph of the operating cost, which is at the end of the day what we were interested in. So the blue is the discharge air temperature, and then the green is the operating cost. So the higher the temperature, the lower the energy cost. So you will see a lot of values or a lot of data in there that is close to zero. So the green one, when you see it close to zero, it basically means that it's just recirculating the air. It's not warming up. It's not cooling down. So it's saving energy there. This is a discharge air temperature versus the energy usage. So again, the blue one is the manual process. So you see, that's why you see that cluster around the same area, because it was always coming back to the same temperature, same conditions. And then you see the two other curves, and the reason why we have two curves is because there's a difference between occupied and unoccupied hours. So the conditions are different. people in the room, they're generating heat, humidity, so that's why you see those two differences there. This is another table for a different air handler. So as you can see, so these two were sharing the same model. And as you can see, the success, I guess, or one of them is operating better than the other. Again, that's one of the things as part of phase 2 that we are looking at. This one did much better. It was on more time than the other, but still kept the humidity a big chunk of time. So it was still successful. It was still saving money to the museum. So they're still happy with it. Again, the temperature graph that we see here, again, all the way on the left to manual process. And then once we turn it on, it goes kind of like up and down, up and down. Now this is condensed, so you see a lot of up and downs, but it's really a little bit more distributed, a little bit more even, a little bit of a smoother curve. Same thing, discharge air temperature versus operating cost. You'll see that there's a lot of instances where the cost is close to 0. So again, we're fulfilling the goal of the project in this case. And then finally, the discharge air temperature versus the energy usage. So basically the same thing that we saw for the other one. Again, we're seeing a cluster around 58 for that manual process. And then we're seeing 3 different curves for when the model is on. This one was generating different curves for unoccupied, 2 different curves for unoccupied, if I'm not mistaken. But that's the same thing as the other one. Yep. What's that? I don't. That might be something with the image, I think. Yeah. Yeah, I don't think that's, I don't recall it looking like that, so apologize for that. Yeah, so I don't think I noticed when I did my trial that it looked like that. So, but yeah, it's nothing relevant in there. Sorry. All right, so let's look at some of the tools that we used. Again, we used Azure products for this particular project. So the first one is Azure IoT Hub. So if you are working with sensor data, for example, Azure IoT Hub by default already has a way for you to send data to Cosmos DB, for example. A lot of the times your data from the sensor is going to be on JSON already, and that's where Cosmos DB shines. So there is a way for you to connect to Cosmos DB directly without having to write any code, actually. So this is a video on how to do that. Uh-oh. I normally have a slide with a prayer to the demo gods, and the only time that I don't have that, this is what happens. And I was like, no, I don't need it. I don't have a live demo. Nothing's gonna happen. And of course, so let's see if we can pull that up over here. All right, so you can see here under message routing in your Azure IoT Hub, there is a custom endpoint. And if you click on add, you have the ability to add different routes, different endpoints to your Azure IoT Hub. So in this case, we have Cosmos DB, and all you need really is the credentials. Those are the other options that you have. So you can send it to a message hub. But all you need is really your credentials to the Cosmos DB account, the database, and the container that you want to send the data to. You got to specify your partition, very important when you're working with Cosmos DB. But after that, you create that endpoint, and that's all you need in order to be able to save data into Cosmos DB. Super simple. You don't have to write a line of code, and everything gets stored automatically. The other component that you're going to need if you're working with this is you're gonna need a route. So you're gonna be able to tell if you have multiple devices, you wanna be able to say, okay, all these devices are gonna go to my Cosmos DB. If you wanna split them, maybe you don't wanna store all of them for whatever reason in Cosmos DB, you can set it up using this a route like the one that I show here. So very simple, no code required, and your data is automatically stored in Cosmos. Right, so let's reopen this. All right, next tool is Azure Machine Learning Studio. So this is a tool that Azure has that allows you to create or allows you to train, test, and deploy machine learning models with a user interface. So you can do anything from, you can do LLM models if you want, you can do custom models like in our case. There's a whole, there's a bunch of different things that you can do with that. So let's look at what training a model looks like. So you see here the section, you have a compute section and, oops, you probably want to see that. There we go. All right. So in Azure Machine Learning Studio, you have a compute section. So you're going to need a compute resource in order to run this training. So you can create as many, well, you can create a certain number of computes if you need. There's a certain quota in every subscription. That's one thing that you need to keep in mind. But normally you probably need one unless you're training a ton of models. A great thing that you can do is that you can specify if you wanted to shut down after it's been idle for a little bit of time, so that's gonna definitely save you money. They're not super expensive unless you're using a crazy powerful one, but still, you know, you don't want to compute running amok, not doing anything. So good thing to do if you are doing something like this. So in the video, I already have it running, but it's super easy to turn it on. And in this case, I'm showing what's automated ML. So this is just a wizard kind of experience for you to load your data, select the different settings for your training, and you know, do the testing, any validation. It does everything for you. So if you don't have, you know, Python experience, you don't have that experience in your organization, this is a great resource. This is a great alternative for you to do that. And obviously works because that, you know, that's what we use here. So I already created an asset or I already have a CSV file with the data, but you can upload data from your computer. You can upload data from a storage container. I believe you can also do data from a database, if I'm not mistaken. But in this case, it's just a CSV. You specify your experiment, so you can create a new one or you can run an existing. So here I'm just creating one for the video, or I'm entering the name for a video. Then just specify your target column, so what are you trying to predict? And then you specify the compute that you want to use. So you can create your compute straight from here, or if you already have one, like in this case, you just got to make sure that it's obviously up and running. Otherwise, you're not going to be able to select it. You're not going to be able to move forward. So next, you specify the problem that you're trying to solve. In this case, it's a straight-up regression problem. So it's already pre-selected for me, but you can see you have classification, time series forecasting, NLP, and then you can also do computer vision. You have the ability to change, modify some of the configuration in here. So the metric that is going to be used to evaluate the different models. You can also choose to explain the best model. So we'll see what the explanation looks like in a little bit. You can specify if you want to just use certain models. If you want to get that deep into the configuration, that's an option that you have. So you'll see there, you can say, I want to block these models from this training run. And you have other specifications about how long you want to run, and if you want to do some concurrent training in there. Over here, you can specify if you want to be able to be specific about the type of feature that you're using. For example, that there has auto as a value, but you can specify numeric, daytime. There's a few different options that you have there, again, if you want to get that deep into the configuration. And then once you click next, you get to the last page. You can specify what kind of validation you want to perform over your data. And you can also specify if you want to split the data that you're providing for this job. Do you want to use some of that to do the testing, to do the validation for the particular model? And once you have everything specified, you just click finish, and goes and runs the job for you. The average amount of time that it took in this case, it was about an hour that it took us to do that training. So obviously, the more data that you have, it might take longer. Also, the compute that you use is going to come into play with that. But an hour is pretty good amount of time. So after the process runs, this is what you will see. So you can go to the jobs. You can look at what the output is for the job. You can look at the different models that it generated. So So those are all the different models, and you can see there with the how they scored. In this case, it's an R2 scored, and then this is the explanation that was selected. So if you click on View Explanation, there's a bunch of different data in graphs that get generated for you that you can look at. So you can look at the top 4 features by importance. You have different views in there so that you can make sure that the training job was successful, and also figure out if you have to adjust anything in the next run, because it might take you a little bit more. You go to metrics, there's a ton of metrics in there that you can also look at if you want to dive deep into the results and how it performed and whatnot. And I'm just going to go to, this is the output logs, but the one that I want to show is the output from the training. So if you click on one of the models, if you go to outputs and logs, it shows you the results of the testing. So what are the predictions when it tested the model that came out of your job? It gives you a CSV that shows you the original value for the humidity in this case versus the predicted value, from your job. That way you can also run analysis there. You can do comparison, how well did it did, how close it is to the original value, and you can determine whether you want to actually use that or not. All right, so I'm gonna skip over here. We already watched that video. And the last tool that we're gonna take a look at real quick, it's called Microsoft Fabric. So this is a relatively new product that Microsoft just released. If you are interested in learning a little bit more than what I'm gonna show here, this is just gonna be like a minute or two. I believe there's a session in the next time slot that dives a little deeper into Microsoft Fabric. What Microsoft wants this to be is a one-stop shop for analytics. So anything that you can do, even they're trying to integrate some machine learning functionality in there. So all of that, they're trying to make this the only place that you go for that. So right now you have Synapse on one side, you have other analytics tools in some other place, you have Power BI. So from here you can get to all those places. So what we are testing actually right now is a new feature that is Cosmos DB mirroring. So this is basically going to create a copy of your data in Cosmos so that you can run analytics into it and you don't have to worry about the cost of querying a Cosmos database. At the moment, it only works for Cosmos DB for NoSQL. I'm assuming they're going to expand it to the other Cosmos DB variants at one point. And all you need is the credentials, so the endpoint and the credentials to your Cosmos DB. And once you click connect, it's just going to start pulling all your data and it's going to put it over here for you to be able to access it and for you to be able to run queries on it. So that is the demo one. I already have another one, like I said, that we are testing. You can monitor the replication. So once you start it, you can see how many records have been imported, if there was any issues with the replication. And then if you click on this SQL Analytics endpoint, you'll see in a little bit that it just loads all the data that you have in Cosmos. So all the different collections are shown as SQL tables. And you can run queries on it. So right here, let me fast forward it. There it goes. So it's loading all the data. So you'll see there that everything that I have in Cosmos DB, it shows, except for that particular column that we're storing it. It's an array of JSON objects, so it doesn't show as obviously separate columns. But then you can run any query that you want, any sort of analytics. You can then build a Power BI report from here. So it is, like I said, trying to make it a one-stop shop for your analytics. So let me fast forward. I made a mistake in that query. There you go, and then like you're querying a regular SQL Server database, except the data is from Cosmos DB. All right. Cool. Any questions about the tools before we move forward, actually? All righty. So we try to watch the video. All right. So lessons learned. Some of the things that we learned, not just in this project, but in other AI or ML machine learning AI or ML projects that we've had. First of all, business stakeholders are key. And you're probably thinking, well, that is the case for any software development project. You need to have a good relationship. You need to have someone that's going to champion the project from the business side. But it becomes even more important, I think, for machine learning models or machine learning projects, because a lot of the deliverables that come out from the iterations, if you want to call it, from a machine learning project is not something that you can really demo. If you're working on a website, for example, if you're adding a new page, if you're adding a new button, that is something that you can demo. That is something that a business person is going to understand, is going to see, okay, that's where all the time, that's where all these resources are going. When you're working on a project like this, especially at the beginning, all the analysis that you might have to do in order to understand the data, in order to put it in a format that is going to make sense and in a format that you can use for the training, that's not something that you can really demo or is going to make sense for someone that is not in the day-to-day, is not up to date with the project. So it's important to have that relationship. It's important to have that person on the business side to champion this, whether it's a partner, whether it's someone internal in the organization or somebody at the client, whatever the case may be, you got to make sure that you establish that relationship. It's going to be very important. This is a case, the next one is a case of do as I say and not as I do. So defining clear goals is going to be very important as well. We didn't really, when I talked about the objective, I didn't really say we want to reduce the energy consumption by 1%, okay? But it's very important, I think, to do that in certain situations because for you, the success of a project might be we want to reduce it by 10%. For me, it might be we want to reduce it by 1%. So we want to make sure that we have an agreement and understanding of what will be a successful process or a successful machine learning model. Otherwise, we're going to end up wasting time. If we don't agree on something like that, we're going to say, okay, well, we're only saving 1%. It's a waste. And it might not be a waste of time, and you can always work on improving that model. But if somebody comes in and says, let's scrap the project it doesn't make any sense. It's not saving us, that much money. So very important to set that from the very beginning, especially, if you don't have a big trust relationship with the client or, with the partner, whatever the case may be. Know your data, very obvious, but if you know your data inside and out, you're gonna be able to accelerate your development. In this case, it really helped us to know the relationships between the different features that we had when the moment came to pivot to the approach of predicting humidity. And if we didn't do that analysis, if we didn't understand the data and all those relationships, it would have been very difficult for us to understand, where do we go from here? This first approach failed. Where do we go? What can we do? How do we solve this problem? It can also lead to faster troubleshooting. There have been instances where the building engineers have sent us a message like, hey, the models are discharging something that doesn't make any sense. Can you guys take a quick peek? And just by looking at the data at that particular moment of time, we can tell, a fan in that particular room is not working properly. You guys should probably check it out. We've actually had instances like that where they found an issue with equipment because of the way that the model was working. If you're working with sensors or any sort of equipment like this, it is very important that you try to do the analysis up front about the differences between the equipment, because that will avoid you having to do changes down the road. So similar to do the requirements gathering in a regular project, if we're working with, in this case, the air handlers, like I said, some are small, some are very big. All those differences are gonna come into play in your project. So you gotta make sure that you do that analysis up front if possible. In this case, we weren't able to do that because we were coming into something that was already ongoing, and we had to deliver something as quickly as possible. But I think if I could do it again, or if I could have been involved in the beginning, from the very beginning on the project, I definitely would have looked at all the differences between those air handlers so that we could prevent it, or we could be aware of all those differences and plan for that. And then finally, be responsible. And by that, I mean, this isn't a project that has a lot of impact on people's life, other than you might be a little cold or a little warm the next time you visit that particular museum. But you have to keep in mind that a lot of the times we get very excited as technologists about what a particular technology can do. In this case, machine learning. We're just thinking about all the different exciting ways that we can use machine learning. And not everyone is gonna be as excited as us, especially if they feel like their job is gonna be in jeopardy, or the process that they've been following for 20 years is gonna change, even if it's not gonna change drastically. So keep that in mind when you work on these kind of projects. Make sure that, if possible, show small gains. Maybe improve the parts that they complain the most about before you do a full replacement of a particular process. I think that will help you do very well. Keep humans in the loop. In this case, we're not trying to replace the building engineers. Again, we don't want to damage our pieces that are millions of dollars. So I don't think there'll ever be a time where the model is going to be running by itself, doing whatever it wants. And I think that should be the case, at least until we get to the point where machine learning can do the reasoning that we can, which, we don't know how long that's going to be. So keep humans in the loop if possible, especially if you're building something like predicting the, granting credit, for example, to people. Make sure that there's a human in the loop that can make some of those decisions that require a little bit more common sense. And then whenever possible, apply safeguards. So make sure that you look at your data, make sure that, as you saw in the first approach that we took, garbage in, garbage out. I'm sure you've heard that before. If you train your model with data that is not good enough, you're not gonna be performing at the level that you want, and you might be generating some output that is definitely not okay. So we've seen that in the past, and especially now that we're seeing machine learning or AI that can mimic a person's voice or a video with a person that it looks like just like you, we have to make sure that we, at the forefront of this kind of big change, that we take as many precautions as we have. So again, if you're working on those projects, keep that in mind. If you worked with Azure or Microsoft in the past, there's a responsible AI principles that you can go look at on some suggestions on what you can do to make sure that you are being responsible with this sort of technology. I have some links. The slides are going to be available in the SearchDrake GitHub repo, so you can go check them out there. And then again, those are my socials. If you have any questions about the project, about the tools that we use, if you want to dive a little bit deeper. I know that I didn't go into a lot of detail about how we use all of them. I'll be more than happy to connect, and I'll take any questions that you might have at the moment. Thank you. Any questions in the room? Yeah. So in this case, we started, like I said, in August, and it took a little bit of time to get some of the data over. But we first turned the models in October. So it was about a couple months, not all of it, full steam with the analysis and all that. So that's how long it took us to get to something in quote unquote production. So that's how long it took for the models to be up to running. Again, if you're using something like AutoML, you'll get there super fast because you don't have to write any sort of code. And as you can see from the graphs, it's performing really well, even though we're working on improving it a little bit. Any other questions? I haven't checked the Discord if there's anything. Yeah. What was the last one? Integrate with what did you say? With any other things Yeah, so right now it's just basically that air handler, that AC. And then we also monitor the outside conditions, so we have that information as well. Because the air handlers have the ability to pull air from the outside. So we want to make sure that we have that information as well, because we need to take that into consideration. Whether it's too cold outside, you're going to bring cold air. We got to make sure that it doesn't drop the humidity too much, things like that. So we have that information available, but we're not integrating with anything else at the moment. I don't know if there's plans for something like that. Any other questions? Don't think so? All right. Thank you again, guys. Appreciate it.